Welcome back, student, to the alternating series and the alternating series test. Today we will talk about the error estimation for the alternating series. This is one of the most important topics for engineering students because the whole idea of doing the series is that we want to estimate them somehow because we cannot find the accurate answer all the time. So sometimes we will go back and we approximate. For that, I would like to start with a familiar example, which is the number pi. So I'm sure you all remember the number pi from school. Now the number pi, first of all, we call it irrational number. And what that means is that two things. First of all, it cannot be written as a fraction, So I cannot write it as a over b. That's one way of saying it is irrational. The other way is saying that the decimal representation does not end and does not repeat. Of course, does not repeat in a pattern. So the decimal representation for the pi, which is 3.14159265, blah, 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 this will never end, and we will not see it repeating in a pattern that we can understand. It's not like when I say 3.33333, this is just a repetition of the 3 in a certain pattern. Or if I say 1.25, this is an ending one. So when you say 1.25, this ends. Or when I say 3.131313, this is repeat in a pattern. Now for the pi, none of them happens. It does not end, does not repeat in a pattern, so we cannot really find the exact value, and we cannot write it as a fraction. So we call it irrational. Now, the pi has a very long digits to be written for it, and there are computers which are finding more and more digits of the pi, but at least for the first few of them that we know, is pi is about 314, and then we have 15, let me just write it down close to it, 159 265 358, and the list goes on. 979 and the list goes forever. Okay, now since centuries ago, people trying to approximate the pi. Now, because we are living in a world where we have supercomputers, we can't find all those numbers. There is a formula to find them all, and we can find more and more because we have a very supercomputers. Now the Egyptians, and this is, I'm sure you have seen it in school, they tried to approximate the pi using 2020 over 7. They said that pi is almost 2020 over 7. Now let's see how much 2020 over 7. It is 3.14, and then we have 28, or just let me do it in the white. So it is 3.14, and then the next digit will be 285. Now can you compare their approximation with the actual approximation of the pi? You can notice something, that they are correct up to how many places, how many digits they were correct. Exactly, only 2 digits. So let me just write this down before we forget it. So this is correct up to 2, usually we call it decimal places. Okay, that's how they were correct up to. Now let me go back. After the Egyptians, one of the Chinese people came and he said, okay, let me just do the pi using this number, 355 over 113. Now if you write this number in your calculator, this will be 14 and then 159 and then 29 2 then 035, doesn't matter, and this is the number. Now here you can notice that he is correct in how many digits? 1 2 3 4 5 6. He found the first 6 digits to approximate the pi with. So here we will say this is correct up to 6 decimal places. Okay. Some other people, they try to approximate the pi by taking the square root of the gravity of the Earth. There is a formula in the physics where it linked the pi with the gravity, and they use this formula in order to approximate the pi by taking the square root of the gravity. And if you look at the square root of the gravity, it is of course square root of 9.8, which is about 3.13 something. Now this is fine, this is correct up to 1 decimal places. Now to get a better approximation for the pi, we need more correctness in terms of digital places. I don't need just 1. 1 is bad. 2 is bad. 6 is okay. If you have more than 6, that would be better. And more will be better. And more will be better. So as long we go on trying to approximate, it will be much better. During the Islamic era of mathematics, they have found so many digits even without supercomputer. Now in the 21st century, we can find up to maybe 500 digits, 500 correctly. And that's exactly what do I mean by approximation. So I have a number and then I'm trying to approximate it. Now when you say it's correct up to 2 decimal places, this is the same as saying your error is about 10 to the negative 2, which is 0.001. Why I wrote 2 zeros? It means the first 2 digits are correct. Now, this and this are the same thing, but we always prefer to say this one because it gives you more feeling of which digits that are correct. When you say 0, 0, it means the first 2 digits are fine, and then the third one is not. So in the next one will be the same thing. Let me just use a different color maybe. Here is the error will be point, and then you have to write 1, 2, 3, 1, 2, 3, and then 1. 6 digits. So the first 6 digits, I'm sure they are correct. The rest, they have an error. And in this one, here is just 1. So that's exactly how we think about the error, the estimation, the approximation. So we will focus on the error. The error usually will be written as 0.000, and then there is a 1, maybe 2, it doesn't matter, but just bunch of zeros and there is a number. Now we need to apply this error method into our series. Now you have a series. The series might be convergent because we can check if it's convergent or divergent. I don't know exact the number because I cannot add everything in the series. The series is an infinite. So what I need to do is I need to approximate. And for engineers, they need to approximate based on something. Sometimes 0.01 error is fine for them. But sometimes, especially if it's something that has to be a medical, maybe medical consequences behind it, you need more accuracy. So you need 0.00001. Like you cannot have 5 errors. No, you need more than 5 correct places. So that's exactly how we will do it with the series. And for that, let me just show you the formula that I can write it here for the alternating series. We have seen it for the positive series, but for the alternating series is that the approximation as follows. I will give you the error. What you need to do is take Pn minus 1 less than the error that I'm giving it to you. Now, what you will get out of this, you will find n. And this n will be your approximation. So you will approximate using Sn, which is the partial sum of the series up to n, which is b1 minus b2 plus b3 and so on. If you want, I can write it down. b1 minus b2 plus b3 minus b4, and then to bn. I don't know, maybe it's plus or minus, depends on the series. But you stop at bn, and this is the approximation for the series. So we don't write equal. What I will write is approximation. So this is approximate this, and that's how we will do the error, and that's how we will approximate the series. So I will go ahead in the next part of this video. I will discuss 2 examples. I can show it to you. First example, I will give you a series. You need to check if it's convergence or not. And then I'm giving you the error, which is 3 decimal places. I said the 5, we don't care. Just the most important piece is 0.000. We'll see how we will solve this example in the next part. Thank you for watching.